Section 6.1 is on graphing systems of equations. A system of equations is two or more equations with the same variables. And the solution to a system of equations is that ordered pair that works in both equations. So for example, here we have two equations, y equals negative x plus 1 and y equals x minus 3. These considered together is called a system of equations. The ordered pair 2 comma negative 1 is a solution because when x equals 2 and y equals negative 1, both of those equations are true. There are three different ways to find the solution to the system of equations. You can do it by graphing, and that's what we'll be taking a look at today. You can do it by substitution and also by elimination, and those are future lessons. A system of equations can have one solution, no solution, or infinitely many solutions. If the system of equations is consistent, then it has at least one solution. If it is independent, it has exactly one solution. If it is dependent, it has infinitely many solutions. And if it is inconsistent, it has no solution. So here's a nice little chart from your textbook that shows the possible situations here. So here is a solution that has exactly a system of equations that has exactly one solution. We say that it is consistent and independent, and it looks like this. So the red line represents one equation, the blue line represents the other equation, and there is one solution, and that is this point right here where they intersect each other. Second case has infinitely many solutions. We say that it is consistent and dependent, and the two lines are exactly, when you graph them, they end up being exactly the same line. If that's not real clear, we'll see that in one of the examples that we do. And then the third case is where there is no solution. We say that this system is inconsistent, and these are two lines that are parallel to each other, and they never cross each other, which means there is no ordered pair that exists that would work in both of those equations. So here's an example from the textbook. This says use the graph to determine whether each system is consistent or inconsistent, and if it is independent or dependent. And so here we have four lines that are graphed with their equations labeled there. So the first one is y equals negative 2x plus 3, and that would be the green line here. And then the second one is y equals x minus 5, and that would be the purple line right here. And as you can see, the green line and the purple line intersect in one point. So this system is consistent and dependent because there is exactly one solution. Second one here is y equals negative 2x minus 5, and that would be the red line right here. And the other one is y equals, oh, this is a typo in the book. This should be a negative right here. Sorry about that. That should be a negative 2x plus 3 because that is actually, oh, it's a typo right there. I think they made a mistake here. I think that's supposed to refer to the green line here because it says these two lines are parallel. Okay, let me go back and explain. Okay, y equals negative 2x minus 5. That's the red line here. This should be y equals negative 2x plus 3, which is the green line right here. And those two lines are parallel to each other. You'll notice they have the same slope, and therefore we say that this system is inconsistent. So please do learn that vocabulary: consistent, inconsistent, independent, and dependent. Now, to solve a system of equations by graphing, we need to graph each equation and find the point where they intersect. This point is the solution to the system of equations. That is the ordered pair that would algebraically work in each equation. So here we have three examples. Graph each system and determine the number of solutions. If it has one solution, then name it. So we have the lines 2x plus 3y equals 12, and 2x minus y equals 4. In order to graph these, we need to turn them into slope-intercept form. So I'm going to solve each one for y. Okay, so for the first one, I'll subtract 2x from both sides, and that will give me 3y equals negative 2x plus 12, and then dividing each side by 3. I have y equals negative 2/3 x plus 4. And that's my first line. Second line, I will do the same thing. I will solve it for y, subtract 2x from each side. So I'll have negative y equals negative 2x plus 4. And then dividing both sides by negative 1, I will have y equals 2x minus 4. Now let's graph each of those lines, and in order to make it a little more visible, I'm going to do each one in a different color. I'll do this line in pink, and I'll do this line in blue. Kind of helps me to keep them straight. Okay, so negative 2/3 x plus 4. So we'll begin at 4 is our y-intercept, and then I'll use my slope, and I'll go down 2 and right 3. And because I'm looking for an exact point, I need to plot all of the points that will fit on here, or up 2 and left 3. And in fact, I'm not going to draw my line until I see where they do intersect. Okay, let's graph our blue line. Y equals 2x minus 4. Negative 4 is my y-intercept, and my slope is 2, so I go up 2 and right 1. And I notice that I am heading towards the pink line, so let's keep going up 2 and right 1. Ah, there's my point, up 2 and right 1. And I'm just going to graph until I find the point where they do intersect each other. Now I can draw my line. I'll finish off my pink line here. Okay. And I always like to circle the point where they intersect. So this system has one solution. It's right there, and that is the ordered pair 3, 2. So this one has one solution because the lines intersect at that point 3, 2. Okay, my second example here, I have the two lines 2x plus 2y equals 6 and 5x plus 5y equals 15. Again, I need to write these in y equals mx plus b form to make it a little bit easier to graph these. I guess you could graph them using x and y intercepts, but I like y equals mx plus b. So subtracting 2x from both sides and dividing by dividing by positive 2. I have the line y equals negative x plus 3. And then let's do the same with our second line here, subtracting 5x on each side. And then dividing by 5. I have y equals negative x plus 3. And you will notice that our two lines are exactly the same. As you may recall from previous chapters, you can often write the equation of a line in many different ways. And in this case, these two lines end up being the same, so my solution is just one line. So let me go ahead and graph that here. So there's 3 on the y-axis, and my slope is negative 1. I'll do a handful of points here, and then connect those. And because these two lines are exactly the same, we say that this system has infinitely many solutions. Because actually what's going on is these two lines are sitting on top of each other. So in how many places do they intersect? Infinitely many. So if the two lines are the same, there are infinitely many solutions. And let's take a look at our last example here, and these are already written in y equals mx plus b form, so I'm just going to go ahead and graph them. I'll do my pink one, y equals x minus 6. So my y-intercept is negative 6, and my slope is 1, so that's up 1 and right 1, or down 1 and left 1. Okay, let me do my second line. I'll do that one in blue. Y equals x plus 2. 2 is my y-intercept, and again my slope is 1, so up 1 and right 1, or down 1 and left 1. And as you can see, these two lines are going to be parallel to each other. These two lines will never intersect. So you can tell that by looking at the graph, but you can also tell by looking at the slopes of the lines, because both of these lines have a slope of 1. And you'll recall from a previous chapter, if lines have the same slope, then they are going to be parallel to each other. So this system has no solution because the lines will never cross each other because they are parallel. So in this lesson, we took a look at what a system of equations is and how to solve a system of equations by graphing. We also learned a little bit of terminology to describe those lessons. I'm sorry, to describe those systems of equations.